Great. Thanks very much, Dave, for that introduction, and thanks for the invitation to come here and talk to you about a bit of work that I've been involved in, basically through my association with the Stockholm Resilience Center in Sweden, but also based on the work of the 4 global change programs that Dave just introduced. So what I want to do is just bring up 2 concepts. You see one of them now on the screen, planetary boundaries, and what it might mean for business. But before I do that, there's another concept called the Anthropocene that I need to introduce, because it's on this basis that we're actually talking in the scientific community about planetary boundaries. As you might guess, the word Anthropocene's got 2 things in it. The last bit, the scene, is indicative of the geological time frame of Earth history. You've heard of the Pliocene or the Eocene and so on, the time periods that geologists use to characterize Earth. And the anthropo, of course, refers to us, humans. And this is the proposal that the Earth has moved into a new geological epoch, but one driven by us, not a natural change in the Earth system. So to understand this, let's go back to some hard data. This is ice core data from Antarctica. And just focus on that middle red line there. That's a proxy for temperature of the Earth. It goes up and down at about 100,000 year intervals, ice ages, the bottom bit, the really jagged bottom bit, and those little spikes are the warm periods. Now it's interesting because it goes back nearly 500,000 years, and I've marked on there where we evolved as a species, Homo sapiens, extremely recently in Earth history. But it's important. This is the environment we evolved in that our bodies are adapted to. And we need to go right back to that fundamental level. So you can see we've gone through 2 cycles of ice ages and warm periods. But notice the warm period we're in now, which is on the right, is unusually long. And that's very important because it's only in this period that we've developed agriculture, villages, cities, and civilizations. Now, I've taken the last 100,000 years of that, the last ice age, and blown it up on the next one. And that's an ice core from Greenland, the other pole. And you see that the ice ages, at least in the northern hemisphere, are extremely erratic, a very difficult environment for humans to live in. And in fact, so difficult that we were unable to even develop agriculture. We were only hunter-gatherers. But notice this last 10,000 year period called the Holocene, the present geological epoch we're in. This is, in a way, a planetary sweet spot. It's allowed us to get to where we are today. So that's important. I'll get back to that when I get to planetary boundaries. So we need to know a little bit of history of where the planet has come from and where we have come from and where we fit in to the planet. Now notice that indigenous Australians were really the end point of the first movement of humans, successful movement of humans out of Africa, and eventually arrived in New Guinea and Australia maybe 60,000 years or so ago. Okay, you've heard of the phenomenon probably of climate change, and as Dave said, the international programs actually study global change. There's much more going on at the planetary scale than climate. I'll just show you very quickly. That's the nitrogen cycle, top panel, pre-industrial, bottom panel, post-industrial. You don't need to go through it. Just look at the huge additional arrow coming down from the atmosphere. That's human fixation of nitrogen for fertilizer. We fix more nitrogen than all the natural processes on the terrestrial land surface. All those red dots clustered are large dams on rivers. Virtually every river on the planet does not flow unimpeded to the sea. The only ones that do are in Alaska, Canada, and Siberia. And even some of those are dammed now. None of our major rivers in Australia flow unimpeded to the sea. They're all dammed, same for North America and so on. We've massively changed the hydrological cycle on the planet. Those areas that are colored in are ones that are dominated by human ecosystems, not natural ecosystems, mainly cultivated ecosystems. And they're slowly but inexorably eating away at the last major biomes that could support agriculture, that is the tropical forest. The large areas that aren't colored are either too dry or too cold, and that's, of course, most of Australia is in the too dry category. And, of course, climate is something that you see in the news all the time. That's Cyclone Yasi. You can see the size of that storm coming in on northern Australia. We've seen an enormous increase in extreme events of various types over the last decade or so. The metric we use is the average temperature at the surface of the Earth. And you can see, although it varies from year to year, there's still a lot of natural variability in the system. The underlying trend since about the 1960s or 70s is absolutely clear. It's going up, and it continues to go up. So there are a whole suite of changes to the global environment that are way beyond the bounds of natural variability, and they're driven by human activities. This is what we call global change, not just climate change. When I was with IGBP, the program that Dave talked about, we actually tried to systematize this, and we published a book in 2004 on global change in the Earth system. One way we did it was to take what we call the human enterprise, what we humans do day in and day out, and aggregate it up to the global scale. So if you see the time frame there, each of those panels starts from 1750, which is pre-industrial, just before the Industrial Revolution started in England, out to the year 2000, which was the latest we had data at the time we did the analysis. So you see population, then you see two economic indicators, GDP and foreign direct investment. Then you see some resource use, damming of rivers, water use, fertilizer consumption. Down here you see some other characteristics, urbanization. McDonald's restaurants we used as an indicator for globalization. It's actually a very good indicator for globalization. Those are the number of McDonald's restaurants around the world. If I put the number of countries they're in, the shape would be the same. And the last ones are communication and transport. You can see the shape of those, all of those curves. And you notice that one year stands out, 1950. We fundamentally changed as a species after the Second World War in terms of our institutions, our technology, our economies. It's a thing we call the great acceleration of the human enterprise. So even where there was significant activity pre-1950, the slope of the curve changed, and many of the things we take for granted in terms of McDonald's restaurants, international tourism, and so on, were basically insignificant before the Second World War. Now, I could give you a whole lecture on the history of why this occurred, and social scientists have written many books about why things changed after the Second World War. But let me just go on and try to summarize what all this means. One of the ways people look at the impact of humans is a very simple identity. Population aggregated by affluence, aggregated by technology. In other words, how many are we? How much do we consume? And what's the technology we use? Now, National Geographic did a very interesting visual of this. And what they did is took three axes. You can see the one population's going up to the left on the base, technology up to the right on the base. The vertical one is consumption. And GDP is used as a pretty good proxy for consumption. Now, you see a little tiny wedge in the lower left. That's 1900. And you see a slightly bigger wedge right down at the bottom. That's 1950. All the rest is post-1950. And the box is filled with the stuff that we consume. If you actually look at its refrigerators, airplanes, motor cars, mobile phones are a bit too small, but they'd be in there too. Now, make a comment here that this is globally aggregated and there are huge equity issues. Most of that box is filled by the 20% of us who live in the OECD countries, although that's changing rapidly now. So in the Great Acceleration, really consumption has been the dominant factor of the three. Population growth is important, and we need to stabilize population, but it's consumption that's the real issue. Then what we did is looked at what does this mean for the global environment. So in our synthesis, we used exactly the same time frame from 1750 to 2000, and we looked at 12 indicators in the global environment. The top three are the famous greenhouse gases. The one on the left is carbon dioxide. Then we have ozone depletion, which is stratospheric ozone. That's not directly related to climate or greenhouse gases. It's related to CFCs, other compounds which are released into the atmosphere. Then these two next ones here are the only two that are directly climate related. I could put a whole bunch of other ones up there, but the one there in the middle is the classic temperature increase. It's only Northern Hemisphere because we don't have proxies good enough for the Southern Hemisphere yet to go back to 1750. The bottom six are ecosystems. They're the big element cycles like nitrogen, and then change to ocean, coastal, and terrestrial ecosystems. The one on the lower right I'll talk about a bit more. It's global biodiversity, and that's the extinction rate. It's going up sharply. Now, in all 12 of those panels, you see the shape of the curve. It's unmistakable. And in all 12 of those panels, there is no doubt what the cause is. It's the previous 12 panels. None of that's natural variability. So this is why we're making a case that we're in the Anthropocene. This is a different epoch of Earth history. It's hard for geologists to deal with it because it's happening in front of their eyes. All other time periods have gone back and they were able to look at sedimentary records, fossil records, and so on. This is unfolding as we speak today. So it's a real challenge to all of us in the scientific community to really come to grips with what the Anthropocene actually means. So that's a quick potted history of where we've come to in the scientific community, to all the environmental changes that are happening at the global scale, and why we think we've actually moved into the Anthropocene. My recommendation for the start date is about 1950. And there's a wonderful marker, and that's new radioactive materials that are in the sediments already that only existed because of bomb tests. So they're attributable to humans. But there's lots of other stuff in the sediments already, too. And I suspect about 300 years from now, there'll be a whole layer of SUVs in the sedimentary record, too. Okay, let's talk then about what we might do about this. And one of the concepts that a group of us have come up with and published about 3 years ago is this idea of planetary boundaries. And you've heard other things. Limits to growth was popular from the 1970s and so on. Carrying capacity, you may have heard of that concept. Guardrails, tipping elements, and so on. Planetary boundaries comes from this generation of studies, but it's actually different conceptually and philosophically. It's different in this way. We don't say anything about resources, resource use, the human economy, or anything else. We just say one thing, but we say it very clearly. We live on planet Earth. It has intrinsic characteristics of how it operates, simply from the way it is. We have to learn what those are and respect certain boundaries, or we will go way out of the Holocene, the sweet spot in which we developed. And remember, our physiology cannot evolve fast enough to deal with a much warmer, much stormier world. So it's a very simple idea that you need to define a safe operating space that we know humanity can thrive in, physiologically, economically, socially. Once you respect that space, then there's all sorts of opportunities for trade-offs for developing economies and so on. But once you go outside that space significantly, it may be a fight for survival rather than developing an economy. And we don't want to go there. So the challenge to science now is, can we really define these boundaries? And how certain are they and so on? And that's what I want to take you through just very quickly here. We published in 2009 a paper where we proposed that our first cut is that there are 9 of them. It could be less, there could be more. But after 3 years and a lot of discussion in the scientific literature, there have only been a couple of proposals for more. But most people have been pretty happy. You can see what those are. Climate change is one of the 9. But equally important is biodiversity, which I'll talk about in a little bit more detail because we're talking about natural capital. But you can read what the other ones are. We attempted to put some sort of limit on 7 of the 9, quantify it. 2 of them we couldn't quite get to yet, aerosols and chemical pollution. Climate change is the one that's most well known. We suggested 350 ppm CO2 as the cap, or more fundamentally, no more than 1 watt per square meter in the change of the radiative forcing at the Earth's surface, which is actually an integral of many things that happen to the radiation energy balance at the Earth's surface. Now, we suggested there's an uncertainty range of 350 to 500 parts per million, because there's a debate in the community about what impacts will occur at what temperature range. But we're pretty sure that under 350 will be pretty safe, and we're pretty sure that over 500 to 550 we're going to be in trouble. So there is some leeway there. We made a judgment on all of these that we would take the lower bound of the uncertainty range, invoking the precautionary principle. Well, you might know that we're at 391 parts per million CO2 today. So we're already over that limit. And if you actually think that you want to be really safe, the job is not only to slow and reduce emissions, it's to start bringing CO2 out of the atmosphere, which may be a task for the second half of this century. So anyway, that's the idea there. Of those 9, we think that 3 of them are what we call core or foundational boundaries, and we're working on a paper now that we hope to publish early next year. One of them is climate. It is fundamental. It's the energy balance at the Earth's surface. Lots of things happen when that energy balance starts being changed at a high rate, and they won't be good for us. The second one is the one we're talking about, biodiversity. It's absolutely fundamental. It represents the control panel of life. So all the genetic code in biodiversity shapes and modulates a lot of the processes that we depend upon. Think biogeochemical cycles, think food production, think forestry, think ecosystem services in a broader sense, and I think Steve Cork's going to talk a little bit more about ecosystem services. Now, certainly we can lose some of that because there's redundancy built into the system. But science isn't good enough yet to tell you exactly what we can lose and what we can't lose. So again, we've got to think about a precautionary principle. Novel entities are the third one, and that's going on beyond chemical pollution. We dodged a bullet with CFCs. It could have been much worse if we used bromine instead of chlorine, for example. But we're putting lots of new stuff in. Everyone who's got a mobile phone, we're using new electromagnetic radiation all around the planet. And use of mobile phones is probably killing far more birds than airplanes, cars, and wind generators combined through interrupting navigation systems, and so on. So we're massively changing the system through all sorts of new entities that we're putting in. Why is biodiversity one of the fundamental or core boundaries? Because it underpins that whole range of ecosystem services that contribute to our well-being. This is a pretty complicated diagram from the Millennium Ecosystem Assessment, but it's really important because it starts from the things we value on the right, things that you can relate to. And it says they're pretty directly related to a lot of things that nature provides, most of them for free, out of the economic system. You see provisioning, regulating, cultural, supporting, and so on. But look at this little line underneath. It says life on Earth, biodiversity. That's the control panel function. The fact that you have biodiversity helps control all of the processes that provide those ecosystem services. That's why we think it's a pretty fundamental boundary. So we need something like CO2 for the other boundaries. CO2 is a good metric, so is radiative forcing. We can actually measure it reasonably well. What about biodiversity? Well, we're proposing two boundaries in the next version of the planetary boundaries, the two control variables. One of them is the rate of extinction. That's one that a lot of people are familiar with, can understand as species go extinct. And this represents what we call phylogenetic diversity, or the genetic library of life. It entails all the genetic code, including, for example, the human DNA, animal, plant DNA, and so on. Our DNA controls how we operate physiologically, mentally too, to some extent. So it's important. It's the basis for the continuing evolution of life on the planet. It's essential, as I said, for maintaining the flow of ecosystem services. You've got to have healthy biodiversity to keep redundancy, to keep the services flowing when you get shocks in systems, provide resilience, and so on, and gives us adaptability into the future as things like climate change. The second one, though, is an interesting one. It's called mean species abundance, and I know TEEB has used it quite a bit as an indicator. There's another one that Bob Scholes in South Africa has developed called the Biodiversity Intactness Index, BII. Similar to it, it measures the intactness of an ecosystem. And what it starts to pick up is before a species goes extinct, when it becomes so rare or its range is so contracted, it then becomes functionally extinct. It stops playing the functional role in ecosystems that it had. So it's a more subtle measure of what's happening to biodiversity than simply extinction, rates of extinction. So we need to look at that, because in the shorter term, this is what maintains well-functioning ecosystems, intact ecosystems. Once you start changing them too much or pulling out too many species, you often get nonlinear changes, abrupt changes in the functioning of ecosystems. So we need a double-barreled indicator here, one for the longer-term continuity of evolution on life, adaptability, and one for the shorter-term, more direct flow of ecosystem services to humans, which will probably be most of the focus of the discussion today, which is embodied in ecosystem services, natural capital, and so on. Here's an example of what happens when you lose, when mean species abundance changes. This is in southern China. An example of where a species of bee has gone locally extinct. It's not globally extinct, but it's locally extinct. And the ecosystem service, pollination, disappeared also. And so it's much more costly to have humans climb into trees and artificially fertilize a fruit tree than it is for bees to come in and do it. And yet we don't value this. This would not be picked up by our extinction indicator, but it would be by mean species abundance. Okay, so this is what we're talking about, is free ecosystem services that at present we don't value very much, but are essential to supporting human well-being. What might these boundary values be? Well, rate of extinction, we actually proposed one earlier, and that was 10 times background level. Now, an aspirational one, which we know we can't reach, but the ideal would be no loss of genetic diversity, because we simply don't know what types of genetic diversity we need to go into the future in a rapidly changing world and keep well-functioning ecosystems. We know we probably don't need all of it, because nature's pretty good at putting some redundancy in, but we don't know where that redundancy is. So an aspirational goal is to reduce the extinction rate to as low as possible, trending toward no loss beyond background levels. We know that's not really feasible, so we have a practical one, and there you can have a lot of argument about what that is. We propose no more than 10 times the background rate of extinction. I think there's probably enough redundancy in the system that as we trend towards zero, we can live with that for a while. We got heavily criticized for people who are in the conservation areas saying that's too high, and in an aspirational sense, it is too high. The current value is 100 to 1,000 times the background rate. So no matter how you cut it, we are way above what we think is an acceptable rate of extinctions. And by the way, business as usual would take us to another factor of 10 more than that this century, with climate change playing an increasing role. Most of this, by the way, is not driven by climate change. It's driven by land use change. It's driven by invasive species, all sorts of things that you're probably well aware of. In terms of mean species abundance, we propose a boundary of about 70% of the original mean species abundance. And that's based on what we call a soft threshold. There is a lot of literature out there saying there are tipping points within biological, ecological systems. There's a lot of debate about where they lie. Most of the literature says somewhere around 50% loss before you really start interrupting the flow of services from ecosystems. But there's a lot of uncertainty around that, from 30 to 70%. So using the precautionary principle, we've put it at 70%. Now there's a TEEB estimate out there that if you aggregate this globally, our current value of mean species abundance is about 67%. So that's indicating we've just gone past what our proposed boundary is, or in other words, we really can't afford to lose much more before we're going into territory where services might be interrupted. These are the estimates of the background rate. This is from the Millennium Ecosystem Assessment on the left. In terms of marine species and mammals, 0.1 to 1 species for every 1,000 species per every 1,000 years when extinct. So that's the natural rate. It's pretty slow from a human lifetime perspective. Here's where we are now. You see we're at 100 to 1,000 times that background rate. In the right-hand panel is a modeled extinction rate for the future where climate change becomes more important. It goes up by another factor of 10 to a factor of 100. So we're saying that we've really got to avoid what happens in the future, and we have to get the present one back down towards the background rate. The last thing I want to leave you with is this idea of abrupt change or tipping elements. And they're actually really well known in nature. Anyone who studies ecosystems tells you this is actually very common. In our Australian ecosystems, we see it all the time, particularly in what we call savannas, where they're mixed grass, woody species, where if you increase the grazing, it's fine. If you increase the grazing just a little bit more, it flips to a woody-dominated species. This is actually common in marine systems too, so it doesn't surprise anybody. What is interesting is people are now starting to analyze global biodiversity, looking at the past 5 mass extinction rates in Earth history. Each one of those seemed to have reached a tipping point where you started losing complexity, diversity at various parts of the world until you reached a critical level, and then the whole global system, the natural system, biological system, flipped to a much different system. Now this is an estimate showing as population increases and pressure on natural systems increases. Those darker green wedges are terrestrial ecosystems that are already showing state shifts. Some of them are absolutely clear shifts because we've cleared land and put it into cropland. That's a state shift done to produce food. But some of them are starting to flip simply because we put too much pressure, either hunting, fishing, toxic materials, invasive species, what have you. And so now here we are in 2011 when this last analysis was done, where somewhere around 30 or 40% of ecosystems have now shown state shifts around the planet. And about 15 or 20% are absolutely deliberate. Those are croplands, which is state shift. And the light green is what we call lightly affected ecosystems. But here's this 50% roughly soft threshold. Now they think this might actually apply globally, so that once we hit maybe later this century with 9 billion people, we may go over that 50% threshold. And then we get a flip down to an Earth where all of the systems are completely changed. Boreal forest, tropical forest, whatever. It's happened in the past 5 times due to natural causes like meteorite strikes. But this is something that we're driving at the moment. So once we hit that, notice that you can't go back up simply by taking a little pressure off. You've got to take a lot of pressure off and wait a very long time. It's what we call hysteresis in science. So basically, this is irreversible. You can see where we are in 2011. So it's not just a matter of ecosystem services, which are very important. It's a matter of the life support system of the planet as a whole. So there's a lot at stake here if this science is right, and there's pretty good evidence from the past that it is. Well, that's just what our overall analysis looked like of the 9 boundaries. This green circle represents where we think the boundaries are for all those wedges coming out. The red indicates where we think we are in 2009. And I think it's interesting that you see climate change, where a lot of the emphasis is now in terms of public policy. But biodiversity loss, in our view, is even more serious in the longer term. And here you see the nitrogen cycle. You see the other ones there as well. Well, I'm going to stop here and just leave you with this little cartoon of what we're talking about. And this, again, this idea of flips, tipping elements in subsystems. You see tipping elements. And one that's been in the news recently is the Arctic sea ice. We've been losing that bit by bit. We now are pretty sure we've crossed a tipping point because the internal feedbacks in that system mean that no matter what we do, that's going to be lost during summertime, probably in the next couple of decades. But we think there might be one for the Earth system as a whole. So when you bundle all 9 of those, biodiversity, climate, element cycles, water systems, and so on, we may flip to another state if we push the Earth too far out of the Holocene. This is what the Anthropocene is all about. Now, it doesn't matter for the Earth. The Earth has been in wildly different states than it has been today, but it matters for us because we're creatures of the Holocene in terms of our civilization. And it's hard to imagine what happens if we move too far out. So I'm going to stop there, Michael, and maybe during the day we can have some discussion on that.